So you'll run into these different types of drawings. Of course, we're down here. We're in line diagrams. But what you'll find out in the trade that we're in, you're going to have to learn how to deal with a lot of different diagrams that you're going to work with. In fact, we deal with, we have a course called AUT 104, which is blueprint reading. We used to call them blueprints, by the way, because that's what they were. The way they made them, they would turn up, the whole print would be blue, and then the lines would be white. Or you'd see the background would be white and the lines would be blue, so they got the name blueprints. And everything was done that way. Most of the time now, we see white on black, but we still call them blueprints. So this is kind of like a pictorial drawing. And like I said, this is very similar to the one when you go out and buy a new TV, you buy a new DVD player or whatever. It literally draws you pictures because they're dealing with basically non-technical people, right? I had my neighbor come over here and he says, Rich, I brought a new DVD player. My TV won't turn on anymore. And I went, his name was Artie, by the way. He passed away. But I went over there and his TV wasn't even plugged in. And he said, you mean I have to have both of them plugged in? So if he thought he plugged in his DVD player, the TV would still work. So that was his exact word. You mean I have to have both of them plugged in? So we have people out there that's very, not technically inclined, and so when they give these new items, they'll draw pictures of the new items. They'll put your TV and everything and show you how to hook everything up to it using a pictorial drawing. But you see the size of those things just when they show you try to hook up a TV, So basically what we do is we basically draw the circuit and we put images of what we're doing. So you can see this is a flashlight. And it's got a picture of the flashlight, it's got a picture of the switch, it's got a picture of the battery, and it's got a picture of the light. So this would be a pictorial diagram of a basic flashlight, whichever every one of y'all have used. This is a pictorial drawing that we just got through talking about. So this is the connection on the back of a TV. And it shows you pictures of what you can hook up to it, right? So this is actually off a TV. I can't remember if it's the one I bought or not, but it's one, I think it's one that I got. It's not new. But this is available, so pictorial drawings, we actually draw what? So audio, cable, camcorders and recorders, personal computers, and anything that you can hook up to this device right here. Okay. That's my last TV I bought, I'm thinking. Symbols are used to conveniently represent electrical components on electrical and electronic diagrams. So instead of putting pictures, we use symbols for them, right? Okay. So this is an example. This is right out of the back of the book. It's in one of the appendixes. So the appendix in the back of the textbook gives you a lot of. It's got electrical symbols. It's even got electronic symbols back there for transistors and stuff like that you might want to look at. But this is some of the things. So okay, so this is a symbol. This is multi-fail, but so the textbook's not even quite right. So what is this a symbol? What's this actually a symbol for? Okay, so that means I don't have a symbol for this device right here. So technically that is the center of that is the symbol of a DC voltage source. Whether it's a battery or this guy right here. The only difference with this guy is we'd come over here and we'd put an arrow through it. Anytime you see an arrow through a component, it means it's adjustable. We got a fixed power supply. So I got these, and you'll be playing around with these a lot, guys. So here's our variable power supplies. So we got a fixed power supply. This is 5 volts. And now notice this guy is good. I don't know if y'all can see that. a nomenclature that is used all the time, and that's in electricity and electronics. And as long as you understand the difference, you're okay by using the wrong word. But no, can y'all see this right here? What does it say?
Common.
What's the difference between a common and a ground?
Well, ground is the earth, and common is something.
Yeah, so this is isolated from earth ground. So it's got a, if I wanted it to connect it to earth ground, it's got a green, y'all can't see it, but it's got a green connection back here, and I could run a wire around here, and I could do what? I could create a true ground. But when you look at the power supply, when you get into the slip-case fibers we got, they call that black lead ground. You can take it on meter and stick it on that one, and you can go to that ground lead, and it's going to measure infinity. So they're calling that ground when actuality is what? It's a common. So that's the problem. That's the problem you're going to run into, is that even people that build and design power supplies will sometimes call a common, they'll call it what? A ground. Like in your car, they'll say, well, the black lead's connected to ground. And of course they're not. So,
Are we allowed to say we're using it as a ground, or call it a common?
no, you can say that as long as you know the difference. You're not using it as if you don't connect it to ground, then you're not using it as a ground. You're using it as a common. You understand? If it's not connected to ground, it's not a ground. So that means there's got to be a rod somewhere, right? So that means if I had a ground on my car, I'd have to have a rod driven in the ground somewhere, and an extension cord was a few miles long so I could drive my car, right? You understand? Like when we was in the Navy, I worked on airplanes, big old patrol airplanes. And every once in a while you'd call and put a gripe in work, they'd have a problem. And the guy down in maintenance would say, well, you need a long truck, you need a fast truck and a long ladder. You know what he's trying to tell us? The plane was flying. we was putting a gripe in work, but the plane was flying. So yeah, you can go out there and work on that, but you'll need a fast truck and a long ladder. So that's a true story too. In fact, I use that every once in a while.
So I got a question. You know what a pad is. So, you know how you ground the aircraft?
Yeah, we grounded ours too because static electricity.
So is that more of a ground?
That is a ground. So it's got a ground clip on the side of the plane somewhere. You clip it on, and there's a big old thing out there where they park the planes. You clip that on there, that's ground. And a lot of times, if you got a blower card or something like that, they'll ground that thing too before they hit. Yeah, so those are good grounds. Yeah, so yeah, that is a ground. We ground, and I don't know if on our planes they had metal straps on the bottom between the main landing gears that would hit the ground while they landed to discharge the plane. So planes charge up when they're flying. And we had static whips on the back of the wings that would flap and discharge the plane. So planes are flying through air, so they're going through magnetic fields, right? You understand? And they build up a big old charge, you know. And every once in a while it does discharge to, they call it they call that light that goes down through the plane every once in a while on the big planes anyway. So that's a DC voltage source. So we have two on this one. We have two variables. And they're hooked like this, guys. So if you need, and people don't understand that either. So the way the trainers are wired up, let's see, is so we got two power supplies, and they're both variable. They're both variable. And this right here is common. Really common. And then this comes down to the thing, and this is your variable plus, and this goes over here. This is your variable minus. So they got this one red. Oops, red. And then this is black. And this is yellow. So it says, 0 those, but it's actually around 17. And you never get 0. Most of your most of your variable power supplies, you'll never get them down to exactly 0. This one puts out around 2 volts. So that means, if we go between here and here, we get approximately 15. If we go between here and here, we get possibly 15, but it would be negative. If we go across here, if we put our load all the way across there, then we can get up to about 30 volts, using this as minus, without a common. And you can adjust them too, because they're hooked up series 80, right? Does that make sense? So this is a, let's see, this is a thermocouple, which we'll talk about. This is a photoconductive cell, but that's not the symbol. This is a symbol of an AC voltage source. And of course, if we put an arrow through it, what does that mean? That's adjustable. So that would be this guy right here. We don't get AC out of these. These are truly AC, DC trainers. I mean, DC power supplies. This right here actually gives us 3 different waveforms. It gives us sine wave, it gives us a pulse waveform, and a triangle waveform. And we can show you all those. This is a symbol of a photoelectric. This is a photoconductive cell, or what most people refer to as solar cells. And this is a symbol of a limit switch, normally open. This is a symbol of a limit switch, normally closed. Now, limit switches, when you park your device, sometimes the device, when it's at rest, is sitting on top of a limit switch. So what happens is if it's a normally open limit switch and it's sitting on top of it, then we would use this symbol here. Now what you do is what you can do on these things is you can look and see what gravity's trying to do. So gravity's trying to open this one, so it's normally open, right? Gravity, we come over here and now notice it's below. So gravity's trying to open it, so it must be what? It must be held closed. Does that make sense? Then I come over here to my normally closed. Gravity's trying to close it, and it is closed. If I come over here and draw it above it, gravity's trying to close it, but it's open, so it must be what? It must be held open. Y'all understand that? So when we draw this, usually the symbol is drawn according to where it's at when the machine is parked. Everybody understand that? So usually when you have a machine that uses limit switches, when you turn it off, it's going to be up against one of these limit switches. And it'll be what we call the at rest or the normal position. This is a foot switch. These are pretty good pictures. This is a normally closed foot switch. Let's see. This is so this gives people in this problems class 2. Technically, if you don't put a dot, it's what? It's not connected. So that means when I draw these circuits, I'm going to put a dot there, I'm going to come over here, I'm going to put a dot there, I'm going to put, by the way, usually terminals are drawn with an open, right? You understand that? And then I might put a dot right there and come down and do a fill in. But if you don't put the dot, then in this class, if you don't put the dot, what does it mean? It's not connected, right? This was a technique we did, and it's still the way you're supposed to do it. Is that used to we would make copies. Now our printers are so fast and so reliable. We usually don't make that many copies anymore. Well, we do in this class. But if you make a copy and then you make a copy of a copy and a copy of a copy, then sooner or later wires will disappear, and that's still true today. But luckily, we always use the original to make the copies of it. But that would happen all the time. This is a symbol for ground. This is technically, they don't show it in the book, this is a symbol for a common. Let's see, a lot of people don't even use that symbol, right? You'll see this symbol all over the place, even though it's wide. It's technically not the symbol of a ground, of a common. So what else they show us? Everybody okay so far? Great. And they got the power leads drawn a little darker, but you'll probably, sometimes you see that, sometimes you don't. And then we talked about the single post, single throw. We talked about that. Everybody okay there? So we got several. So this would be a single post, single throw, right? This would be a single post, double throw. Okay. This would be a need to redraw this guy. Sorry. I should draw my first one. Then what we do is we dash lines, which indicates they're switched by the same operator, right? So what would that be? It's gonna be what? Yeah, double pole, single throw. Good. And then one place they drew it kind of weird. That would be a what? Yeah, double pole, double throw. That's about as far as we go with these switches. After that, they move into what we call selector switches. This is a symbol for a single-phase motor. This is a symbol for a multi-speed single-phase motor. We've got one of those up here. This is a symbol for a three-phase motor, and it doesn't differentiate it whether it's delta or Y. Really, if you don't have if all you got is a Y motor or a delta motor, it really doesn't make a difference how it's wound. If it's a dual voltage motor, though, how you connect it for high voltage and low voltage is going to be a little different. This is a symbol, of course, for an indicator light. This is a symbol for a bell, a symbol for a horn, a buzzer. This is a solenoid. I did show y'all the solenoid the other night, right? A fuse. Circuit breaker, they'll usually put a little knob on it. These are just fuses, guys. And they don't show us the symbol of an overload. What's the symbol for an overload sensor? 2C, a hook, yeah. This is not the overload contact, that's the sensor that's in the motor that determines if the motor don't start. So this is what we call a wiring diagram. So this is not a good example, it's just of a hot plate. What a wiring diagram does, it tries to show you how devices are physically located with each other. And what if you see it with inside this line, now notice the way the line runs. It goes one long, two short, one long, two short. Anybody know what that means? Yeah. Close. Now mechanically they would all be exactly the same size, but this is going between two shorts and a long, two shorts and a long. What that means, they're in the same enclosure. So that means they're in the same box. Does that make sense? So these devices are here. If I was ever draw it with a wiring diagram, all these push buttons, they be together, right? They would be inside that symbol right there. The only got on that they're 9 kilowatts in the same box. That's what a wiring diagram does. It kind of tries to keep the location of the different components where they're at, physically at. Once you've ever been in HVAC, they basically draw things in wiring diagrams. And we'll see where the power diagram is usually drawn as the wire diagram. But we'll see some of those as we go along. So this is a wiring diagram. This is of an HVAC system. I know what that stands for, right? Heating, ventilation, air conditioning. So you notice, I know right off the bat that all this is located what? Yeah, this guy's located together. This guy's located. He's not used to it. And they're trying to give you the basic physical location of the different devices. Everybody okay? Yes, no? So they're not using the exact symbols for us. This is a schematic diagram. Normally, a schematic, we don't draw the common. We use a symbol, right? You understand that? So normally, you very seldom see this guy. And what we'll do is we'll come over here and we'll either use a symbol for a ground or we'll use a symbol for a common. And what you got to understand, and this happens a lot, that represents a wire. The wire's got to be connected, but what it does, it reduces the amount of wires in the drawing, right? You understand? So what we do, we know everything has almost everything in electronics has a common. Well, what we can do is we can take that wire, instead of drawing that wire, what we can do, we can use the symbol that represents the wire. And you'll probably hear this when you're taking DC. Somebody's going to say, well, I thought that was in the trainer. So they're going to think that's there automatically, right? You understand? But that symbol does what? It represents a wire. And what you got to do when you wire the circuits up? You got to run a wire between all those components. In a schematic diagram, components are laid out so the circuit is easily read rather than showing you the actual position of the components. So the wiring diagram it still uses symbols, but it tries to give you basic physical location of the components. A schematic don't. So if you got R33 on your schematic, and here's R32, it don't mean R33 is going to be the next one on there, right? You understand? So it's very, very different than what we do. So, you know, R43 might be here, and R44 might be up here in the right-hand corner. But what we're doing is we're drawing it out to make it easier to trace. Schematics over here run from left to right. So inputs are over here, outputs over there. That's the only thing that's standard between that. How they lay things out, they're going to try to lay things out. When they make a printed circuit board, they're trying to make it with the least crossing lines they could possibly have, because if you got a piece of metal that's your trace, we call it a trace, you can't do what? So insulated wires, we can do what? We can lay them all over the place, but those metal things on a printed circuit board, you can't do that, right? Microprocessor motherboards are about like 7 layers, and that's the reason they got so many wires that's got to go different places. They're about 7 layers thick. One of them is usually a ground layer, by the way, to keep the boards from coupling between each other. So this is a typical schematic. So this is a power amp, by the way. So input here, output there. That makes sense. Now look, they could have replaced this. Well, the problem is they'd have to redo something, because why did they draw this line right here? Yeah, but why did they use the common? Well, the common is separated by this component right here. So that means that this guy right here is not connected there, right? You understand? Yes or no? So I can't use the common. If I use the common symbol right there, then that means it's not on the other side of that capacitor right there. So this guy right here keeps this from being a common. Everybody understand that? So we can't use it. It's a common for that circuit, but we can't use it, right? Y'all understand what I'm saying? Because we've already dedicated where? We've already assigned it to that lead right there. And they're not connected together. So if you see the common symbol, it means everything that's got that symbol is connected together. These are not connected together because of that capacitor right there. So these are transistors, guys. These are bipolar transistors. TNT and TN. These are capacitors around here. This is the Zener diode right there. Usually if they, normally, I use a symbol right here for capacitors. Can you see what I'm talking about? Especially in this class, because we have this symbol right here that we use for normally open contact. That is not a capacitor. And notice this guy right here uses exactly the same symbol, but it's not a normally open contact, it's a capacitor. Normally, if you see this, this means it's polarized, which means it's going to have a polarity on it. One of them's going to be marked positive, or one lead's going to be marked negative. And if you put it in a DC circuit backwards, guess what it can do? It can blow up on it. Yeah. These are the symbol for non-polarized capacitors, which means you can hook into each other's anywhere. Are we okay? So here's my stereo right there. So this guy's giving us this. This guy's giving us this, and together they give us. I'm doing a sine wave. Audio's real weird. It's all over the place. So okay, so that's the schematic. So if you're gonna work on, electronic components to a component level, you would have to know these symbols. You would have to know how to read them. A line diagram consists of a series of symbols interconnected by lines that are laid out like rungs on a ladder to indicate the flow of current through the various components. And so this is what we got. So we're going to be dealing with line diagrams. Sometimes we call it, later on we're going to learn about logic. So we can connect contacts to do and, we can connect, we can do or. We could figure out NOR. It takes a little long. NAND. It's a little harder to do with that. And then we're going to do comparators. We're going to do an exclusive OR, an exclusive NOR, which is not covered in your book, but we'll make sure we let y'all understand those because those are used a lot. We're coding these symbols. We've already looked at this, right? Everybody okay? Any questions? So what's the symbol for? Well, we can't say relay because a relay consists of two things. It consists of a coil and it consists of the contacts that's controlled by the coil. So this is a symbol of a relay coil. Very seldom in industrial controls are you going to see motors, except little tiny motors, inside the control circuit. Why? It's called a control circuit. It's in there to control things, right? You understand? Our motors are going to be high power things. They're not going to be inside our control circuit. Our control circuit is usually going to be a lower voltage. What advantages the low voltage have over high voltage? Safer. And all our high wattage devices are going to be where? Over in what we call a power circuit. Now we can have contacts controlled by that relay in our power circuit. In fact, I know it is because I know it's a motor starter because of these guys right there. That tells me that relay runs a motor. As soon as I see those contacts, I know that relay runs a motor. That needs overloads. A lot of times your overloads are built into the motor, especially on your house. So just about all motors up to very, very low fractional horsepower motors. You have to have an overload. So your motors in your HVAC system, your motors out there on your washing machine, your dryer, always all have an overload, but they're integrated into the device itself. So this is a stator. This is a multi-speed single-phase motor, so that's why it's got all the leads in it. And there's the overload right there. It's a thermal overload. So it's built into it. It's thermal. These guys will get you hurt because they'll trip if it loads the motor, and when they cool down, what will they do? They'll reset. They reset themselves. So if you're in on a blower motor and the motor's not running and you don't pull the disconnect, it might be because it's got an overload, right? And then when it kicks back in, if you got your hands inside there, you're going to be hurt. So yeah, there's the internal overload. Bigger motors, especially big motors, usually have external overload. That are what? Number one, they're the three speeds are the different colors. The brown wires are for the start protection. So I know over here, I know we got a motor, and I know it's got overload sensors on it that controls these contacts right here. And it's a three-phase motor, so we should come in and angle them in and bring them in like that. This guy, the relay is given the name M. So I'm going to come up here and give these contacts, I'm going to call them M. Then normally we'll come up and we'll have fuses right here. We might have a disconnect up there where we can like ours has got a major disconnect up there, right? Okay. So this is a relay coil. This is the coil. You can't say it's the relay. Why? It's the coil because the relay consists of two things. Well, it consists of the coil and the contacts that are being controlled by the coil. Everybody okay? And we'll use the term energized. So if we say it's energized, it means that magnet has jerked those contacts and made them change directions. So here we know that this contact right here is being controlled by M. It's a normally open contact. And this contact right here is being controlled by M. It's a normally closed contact. And these contacts right here, which are in my power circuit, are being controlled by M. And that's the nice thing about relays, is over here, this can be 26 volts AC, and this over here could be 660, right? You understand that? So relays, what the voltage you're controlling with your contacts does not have to be the same voltage you're controlling with your coil. It's just like when you go back there and flip that light switch, you're not 120 volts, right? You understand? But you can flip that little thing and control 120 volts. Or you can flip that little thing and start a lawnmower with it. I knew another guy, his starter went out, his ignition switch went out on his riding lawnmower. And guess what he replaced it with? A light switch. So it's rated 115 volts, 15 amps, which is good for bringing in a starter coil, or a starter relay. So worked fine. But it was, and he was the kind of guy, kind of like me. The seat started tore up on him, so he got a kitchen seat and took the legs off of it and mounted it on his riding lawnmower. So he had a kitchen seat on there and a light switch to crank it with. So, and that's what's so nice. So what you control with that light switch, it's just a switch. It's rated at 15 amps up to 150 volts or 250 volts, guys. I'm sorry. So what can you run with that? Could you run DC through that thing? Sure. Yeah, sure. It's just that you don't want to exceed what? You don't want to exceed 250 volts at 15 amps. If you do, then it's not guaranteed to open the circuit anymore. So yeah, so most control circuits, and of course we won't start off with that. We're gonna get basic circuits. We're gonna understand logic. We're gonna do ands. We're gonna do ors. We're gonna do nots, and that kind of stuff. And we could figure it out, right? And we'll show you. It takes a little bit to do the nands and the nos. And of course, this is a symbol of a light. So we talked about this circuit. People call it memory circuits. They call it a seal-in circuit. We see these all the time. So what it lets a person do, they can come up with a glove on, hit a button, right? You understand, in a motor start. And they don't have to flip a switch or anything. They just hit a button. And then if they want it to stop, they hit the stop button.
Where's the common in that?
Well, technically, we consider this right. L2 is considered to be the common. So that's why when we look at ours, this guy right here is fused. Now, a lot of industrial controls will fuse both sides. So normally, when you get up to a certain voltage, you have to fuse both your neutral, your common side, and your power side. So yeah, so this is L2 is considered the common. So this is our circuit. So this is the common. And of course, this is one circuit. And this is the other circuit. And we call these what? These are referred to as rows. We'll show you always as we go through how we industry standard on how to number things. Are we okay? Yes? So this is a line diagram. This is US Steel right here. So this was, we taught a class for US Steel. I worked out there for about 4 years probably. I was an electronic repairman out there. I got laid off when they built the pipe mill. So they had to shut the whole plant down with the big pipe. So I started teaching here then. So a little history. And I tested and everything for the pipe mill. And I was supposed to start in September. And the week before, they gave me a call and said, industrial print is due. And this is something that we'll learn. So one thing we'll have to learn is that in motor controls, we don't deal with rung numbers. We deal with line numbers. So what we do when we set it up is, here we go. So every horizontal line that lines up gets the same number. So since these are in line, they get the same number. And it's 137.01. Okay, that's 01. So this is the 137th page of this diagram. And then what they do is over here, they give the relay a name. So over here, we're gonna come over here and put like an M in there, but in the industry they can't do that. So they're gonna give it a name, and they try to give it a name on what the relay controls. And I'll run this off and give it to you guys because we're gonna have to learn this. But what they do is over here is they give you a sheet that tells you what each one of these little mnemonics stands for. Like 5D, DB, number 5 bridle, dynamic braking circuit. And then we have what we call wire numbers, and that's what these are right here. These tells the electrician how to do that. So what they'll do on the terminal boards, every time it comes to a terminal board, they don't put the wire, on airplanes, they put a wire number about every 6 inches. And it's actually burned into the insulation. So all the planes I worked on, all the wiring was white. Yeah. And then it would come in, but it would give wire numbers, and every wire number would be about every 6 inches. It would be on the insulation. In industry, they don't do that. They usually run all the same color wire, But every time it comes to a terminal board, they'll put a little a label on there that gives you wire numbers. So it's a little different. They just, you know, all the wire was, every bit of the wire was white. So this is a line diagram. This is what you'll run into in industry if it's drawn right. What this over here, this shows us the line numbers where the contacts of this relay are located. Because the contacts can be anywhere, right? They could be in any line. So that tells us where they're located at. So we know exactly where we go. We'll give this out and we're going to go into it in more detail. But this is actually U.S. Steel. We taught a class for U.S. Steel. They sent their electronic repairmen, or people that wanted to be electronic repairmen, and they had y'all know where the building is up on the hill at Fairfield. That used to be where they taught classes at, and they decided to go to all computer classes, where students sat over there and they used the computers all day long, and they sat over there for a year between their work. And I had like 18 people, and when they got through, nobody passed the electronics test. Nobody out of the whole group. So they decided to bring them all out here, and they were out here for 4 weeks, 8 hours a day. They paid them for 4 weeks, and we taught them, and there was all but 2. When they got through, all but 2 passed. One guy decided not to take it, so that didn't count against us because he realized that he'd make less money if he got on his electronic repairman. He was like an operator or something out there. And then we had one lady that had to drop out because she was having a child. So that was the 2 people that didn't make it. So this is what we call a one-line diagram. This is very, very stripped down because they take for granted, you know it's got to have a what? Starts with a C. We know it's got to have a common. So they don't even use a symbol for a common. They just leave the what? They just leave the common off. They know that you know enough that nothing works without 2 wires on them, right? So they just leave the common off, and it's up to you to make sure you do that. A lot of times on a 3-phase motor, they don't even want to draw 3 phases. They'll put 3 phases up there. And that way, the electricians know there's got to be what? You got to have 3 wires under there. Let's call a one-line diagram. Care must be taken when using electrical symbols to design or communicate electrical circuit operation because electrical circuit operation may change and hazardous situations may be created just because you used the wrong symbol. We got an inverter. We worked on a thing over in Inslee before they shut it down. We called it the Curve Master, and what it did is it used an induction heater to heat up the crown of the rails. It would heat them up red hot, and then it would quench them, then it would cool them down at a certain speed with air to temper the top of the rails that were going to be used in curves. So that's a lot of pressure a train puts on the curve, right? You understand? Originally, they used MG sets. They used big motors to turn big generators because they were taking Alabama Power, which is at 60 cycles, but the induction heaters worked off 600 cycles. So they used MG sets, motor generator sets. After a while, they upgraded and they went to inverters where they'd take it and convert it to DC and re-oscillate it at 600. When they drew the schematics for the things, they drew all the electronics was done with OR gates. And we were looking at that and we said, there's no way in the world this is going to work. Because every symbol the draftsman drew was OR gates. And we finally got the boards out and we had to look the chips up, literally look at the part numbers on there to figure out what it was. So undoubtedly the draftsman only had one template that they were drawing. Yeah, we was looking at the diagrams. He said, man, there's no way in the world this thing's going to work. So every logic gate in the whole circuit was, that's before we had processors, by the way. So everything was done with discrete devices. We already looked at limit switches. We okay? So y'all okay on the normally open, normally closed, normally open, held closed? and normally closed to L open. Because these will be on test. Are we okay? Yes? Okay. An electrical circuit includes, we already talked about this, so basically electrical, we have to have a power source or some type of voltage source, right? Okay. What else do we need? Gotta have a load. Gotta have a path. You gotta have the conductors that takes, so that's, the only thing conductors are used for is to get the what? Is to provide get the current from the what? From the source to the load. With as least of a voltage drop that they possibly can. And that depends on the engineer making sure they use the what? The right material, the right gauge, for the right length, and then temperature that it's going to operate in. Okay, we looked at, everybody okay for the fuse? This is a symbol for a fuse. So this is kind of like we're going to do. Of course, we're not, they're going to draw it, but ours are going to be isolated. So that means we don't have to worry about getting against the ground or anything. So we're going to run, as soon as so on this side, these guys over here, so I think ground's on the top. Y'all have to look. And I think it's L1, L2, L3. And then what we're going to do is we're going to choose two. We'll try to split it up because we don't want to load down one phase, right? So let's just use L1 and L2. And we're going to come up here and we're going to go to a transformer. I'm going to let it go. And we're going to come up here and we're going to so we're bringing in 208, which is low voltage for the transformer. So let me erase this. That's the problem. I'll take a break in a second, guys. There you go. So how's it labeled? So we got what? We got H1. Let's put H1 on the other side. No, this is H4, right? And then what we do, we bring this one up here, and this one right here, and then this will be H2, and this will be I'm sorry, I went the wrong way. I'm just seeing if y'all was paying attention. This is H2, and this is H3. Now, what we're going to do is we're going to bring L1 and L2, and I'll bring L1 over here. It doesn't make any difference which side you go, by the way, on this. And then we're going to come up here, and we're going to put a jumper between here and here, and between here and here. So we're going to hook them in parallel, right? Everybody okay? Then this comes out on the bottom side, and switch to black. And this goes to a fuse. It's actually mounted on the transformer. It's a 1 amp fuse. And they're going to call this XL. And they label this as X2. So which one's going to be our control L1 and our control L2? So when we look at our diagrams, we call it, and this gets people confused because our diagrams use L1 and L2, and then over here on our disconnect we got L1 and L2, but they are not the same. The L1 and L2 on the disconnect is 208 volts, right? Almost 210 volts. The L1 and L2 for our motor control circuit is 120 volts, so around 117. But the transformer is an industrial transformer, so in a transformer, the one with the highest leads are called the what? High side. The one with the smallest number of the smaller loops is called X. They don't call it L for low because L is reserved for inductors. And they don't want you to get confused, right? You understand that? So the transformer's level XL, because this right here is actually X1. Well, that's X1, but we go to a fuse, so they give it a different name. They call it XL. Okay. So what's going to be our control L1 and our control L2? So are we going to fuse the hot side, or are we going to confuse? Are we going to fuse what we call the common side? We're going to fuse the hot side, right? That's just like your house. So your house, your white wire comes in and hooks to ground. By the way, it hooks to the ground level. The circuit breaker is in what we call the hot, which is the black side, black wire. So we'll come down here, we'll come over here and drop down, and this will be RL1, and we'll call it CL1. That's what they should do in CL2 for control, right? But they don't in the book. And then we come down and we hook our circuit up. It's a very simple circuit. So we got a momentary normal push button, and over here we got a light, and then we hook that to L. So your circuit runs between what? L1 and L2. Control devices are connected between L1 and the load is connected between L2, unless we got a motor starter. The motor starter is going to have the what? It's going to have the overload. But you don't wire that. So if I come over here, if I come over here and see this, and then they come over here and put the overload there, then they come over here, you don't wire that wire. So you're going to wire it where? Over here, right? You understand? So as far as we're concerned, this is the load right there. That's the load. So the load the load is connected. The load is between the control devices and L2. And that's a run. Very simple run. This would be a pictorial diagram. That would be a line diagram. Very, very simple thing. Except on ours, we don't have a ground. Are you okay? All right, guys. Let's take a 10-minute break. So the PowerPoint should be in that chapter, electrical diagrams and symbols. I think it's the name of the chapter. So we're going to do that. This is not quite correct. We'd never draw the load all the way over in the center. If you ever look at a line diagram, no matter what you put over here, the load is always over here. Now this actually shows a motor. We're not going to use any motors inside our line diagram. Like I said, very seldom do you see motors. You might see little fractional horsepower motors. We have a cycle timer, which basically has a cam on it. It has a little old tiny motor that spins and actually causes and that would be inside the line diagram, but it's going to be, micro horsepower. A line diagram may be used to illustrate the control and protection of a single-phase motor using a manual motor starter with overload protection. So we actually got one of these somewhere, guys. It looks like a wall switch, but it's actually what we call a manual motor starter. Now, if we use the term motor starter, it means it's got overloads. Contactor is basically a relay that can handle a lot of power, but it doesn't have overloads. And then we have control relays. So a control relay, its contacts never leave the control circuit. So it's going to be a little small relay, right? and you'll run into a lot of these. And you'll find out that, and this is one of the things that that we eliminate with programmable logic controllers. All your control relays are programmed in a PLC. Not your power relays. We still have the power relays, right? But all the control relays. And once you get into extremely complicated diagrams, about 90% of the control is nothing but control, making sure everything's in the right place at the right time before it turns on the watt, turns on a motor or moves something. I'll see if I can find this. I know we got it somewhere. We tried to. An electric motor on a sump pump can turn off and on by using automatic control. So what they got is they've got a float switch. So this is another symbol they're looking at that they did show it. All these symbols are, by the way, are in the appendix of the lab book. So I mean, not the lab book, the textbook. It does a really good job. So we got a float switch in our commode. It's just that it's not turning off electricity, it's turning off the water, but it's exactly the same thing. You know, you've got a valve in there, and when it raises up, it closes, it cuts the valve off. Well, we're doing the same thing, but now the float switch is controlling the contact. So this is a sump pump. So they got the sump pump mounted, you know, I don't know if y'all have ever seen this. A lot of basements, especially that has a tendency to get water in them, will have a hole somewhere, and then it'll have a drain in it, and the pump is down inside the drain somewhere. And that's all it's looking for. So if you get water in there, it automatically turns off and pumps stuff out.
We usually do the work. I've been back in the tank and grows, and we have a lot of tanks for that. These are where they start getting full.
Use float switches, yeah, and drain, yeah. A normally closed contact on a float switch may be used for a pump operation to maintain the certain level of water in a livestock tank. I guess you could do it in a swimming pool too, but normally you just fill it up with a hose pipe. Everybody okay on these solenoids? So we got two types of relays. We have a solenoid relay. They called it a plunger, but technically it's called an armature. And this looks like it's AC. How do I know it's AC? Laminated. Yeah, it's laminated. So anything that's going to see a change in magnetic field, instead of inducing that current in there by induction, right? Y'all saw my little transformer. We break that circuit up. We break it up into little plates. A DC relay, that armature is going to be a big chunk of metal because we don't have to worry about inducing that voltage, right? But AC is going to be laminated. Your AC relay coils are going to be laminated. This got a plunger on it. We connect contacts to the plunger, and then when that thing moves, it's going to open up normally. It's going to close normally open contacts and open normally closed. Everybody understand that, right? Are we okay? So I can pass this big one around to you. The other type we have is, I think I got it in here. If I don't, I should. It's called a flapper. I think it's in that other lecture side. But what they do is you have an electromagnet, and then it'll have a thing on it, and then it'll have a flap on it like this. It'll be spring loaded. Either the spring will be up here, and then it'll actually change the contact. So we have the flapper type. You see that a lot on little old tiny control relays. They don't have to handle it, but your big ones are not going to use that. Your big ones are going to use the armature. And what returns them is either going to be a spring or it's going to be gravity. So certain relays have to mount in a certain way, right? You understand? So you can't take one that uses that armature and do what? Mount it sideways. So this is a good picture. So this is a solenoid. We call this the coil. So it's going to have wires going to it, right? And then, of course, what we put up here, guys, so these would be two normally open contacts on there. And, of course, one circuit would be they don't quite. So one circuit would come in here, and the other circuit would come out here. So when it closes, it'll, like current flow too, right? You see that? That makes sense? Yes, no? It's drawn kind of weird. They got it drawn weird. But a contactor, so a contactor is a relay that can handle a lot of power. Now, it might have what we call auxiliary contacts on it. And these auxiliary contacts go in the control circuit. Then we have power contacts that go in your power circuit. But a contactor will not have overloads. So technically, the relay that runs energizes your compressor on your air conditioner out there, it is not a motor starter. You used to have one in here. It's not a motor starter, it's a contactor. Oh, here you go here. This is a relay that actually runs the compressor. 240. You can always switch one side. So now that's get into that's actually out of the mix. For the compressor, that's the compressor. And you can actually see the coil on that one. Most industrial relays, the coils are in plastic because you see that magnetic wire has got such a thin insulation on it that if you nicked it, then you would short out some windings, right? You understand? It causes a problem. I think that came off of one of my air conditioners that I finally couldn't fix anymore. So this is a wiring diagram. And this right here is a ladder diagram. So on a line diagram, what they'll do, a lot of line diagrams, they actually put the control circuit within the line diagram. Those things get pretty complicated. A lot of times, and you'll see this done a lot on HVA systems, but usually hopefully they put the ladder diagram up there, because the ladder diagram is drawn the way the circuit logically operates, right? So it's easy to figure out. Wiring diagram, when they put the control circuit within the line diagram, all I know is this relay is set to control this line right here. That's all I know. But they draw it across the line right there. The electrical operation of a contactor can be shown using a line diagram, a pictorial drawing, which will be this guy, and then a wiring diagram. Which one's the easiest to read?
Wire diagram.
This guy?
I can read the wire diagram.
Well, what you're trying to, now, we've got just one control circuit. So what they do on this line diagram is they include the control circuit within the wiring diagram. In motor controls, the power circuit and the line diagram are two separate entities. So normally, most of your troubleshooting is up in there. Or it's over here. But when they combine them, it can get what? Get confusing. Yeah, you can get lost inside of a wiring diagram. I wish I had a good one. I need to go out there. So this is getting a little more complicated. So here's this guy right here. So this is a memory circuit. Right? You understand that? Here's the same memory circuit inside a line diagram. Inside a wiring diagram. So I know these are mounted in the same thing. That's my stop button. That's my start button. This is auxiliary contact. That's your sealing contact. That's that guy right there. Here's your relay coil. Let's see. And here's your seal-in right here. It's in parallel with the ohm. It's in parallel with this guy. So if that's easy for you to read, then you're better than me. Yeah, but to me, seeing this up here is so much easier. Trying to figure out this and that are the same thing. So a line diagram shows you the logic of the circuit. It shows you how it logically operates. It don't mean that's the way it's wired. I mean, they're not physically connected together. Yeah.
Oh, I'm correct.
Yeah. What?
I'm looking at it like, how can that one tell you which wire or which, you know,
Well, we come up here, we'll number the wires. We may call this wire 1, we may call this wire 2, we may call this wire 3. This is still wire 2 because it's electrically the same. This would be wire 3. This right here would be wire 4. So your wires would be numbered if you wired it up. You should number them. So anything that's connected together gets the same number. So we'll look at later how we number wires, how we number rungs. So you know exactly when you, on a ladder diagram, you know exactly where the relay contacts are, because they're going to be drawn in rungs, right? And they're going to consist of lines. So this right here would have 2 lines. This would be line 1, and that right there would be line 2. In motor controls, we number lines. We don't number rungs, we number lines, which gets people in PLCs confused, because in PLCs, they don't number lines, they number rungs. And then Siemens don't call them rungs, Siemens calls them networks. So, auxiliary contacts, we talk about those. So auxiliary contacts are going to be in the control circuit because it's going to be low current, low power. Then your main contacts will be in your power circuit. They're going to be bigger, right? And it's just like the gauge of the wire. So what determines the resistance? It's the gauge of the wire. So these big contacts are going to be big. I saw some out there at US Steel that the contacts were as big as my arm. I mean, they scare you. They sound like cannons when them suckers close. So we had some cranes. Now most of them are multi-speed cranes. Now most of them use variable frequency AC drives. But when I worked, we had 5-speed cranes, and what they would do is they would switch speeds with big old relays. I forgot the horsepower on the motors. I know the drive motors. They used 2 on each, one drive motor on each wheel. And those things were loud. And they ran those from the ground with a little radio control. So what's our 3 types of relays? We have a control relay. So all the contacts of the control relay will be in the control circuit. And we have a contactor. Contactors are going to, they might not have any contacts in the control circuit, or they can, but they're going to be auxiliary contacts. They're going to be low current contacts, right? Okay. But it is a power relay. It's designed to handle power, but it has no overload. And then we have a motor starter. Actually, we call it a magnetic motor starter. Because we have a manual motor starter also that's got overloads on it. And so we have a manual motor starter. So just instead of saying motor starter, we should call these magnetic motor starters, and the other one we call manual motor starters. These are going to have overloads. And they'll have the sensors in them. So this is the actual sensor. So the motor will come into one of your main contacts, and then it'll come out and go through your sensor, and then the sensor will come out, and then these will control. So all the current goes through the overloads, and it senses that current, but it don't sense it like a breaker does. So a breaker, if it's rated at 15 amps, then by George, if it sees anything over 15 amps, it's going to do what? It's going to pop. If you got a fuse rated at 15 amps, as soon as it sees, it's especially fast blow fuses. We do have some slow blow fuses, by the way, that if you work with If you work with power supplies or anything like that, like these guys right here, you should use Slobo should use it, because it's got all these big capacitors and everything on there, and they got to charge up when you first turn them on. And if you put a fast flow fuse in them, this odds are the first time you turn it on, it'll probably do blow the fuse, yeah. But the overloads allows the motor, it allows the motor to pull over its run current for a certain amount of time. So it'll allow it to do what? It'll allow it to start. But if it stalls or it doesn't start, then it'll kick out your control circuit. Are we okay? That makes sense? Like that motor right there, that sucker right there is kind of dangerous, ain't it? So on this one, if the overloads kick, you have a watt on. You have a reset. You have a reset. That right there, if it overloads, it could reset what? Automatically, yeah. And if it's a blower motor and it's got all those vanes in it, and you got your hands in there, the motor's not running, and you leave power on and that thing kicks on, you could really get hurt on it. But it protects the motors. So overloads are not in there to protect you. They're in there to protect this big investment motor. I don't know if y'all I don't know if they sell it. They used to sell them down at Lowe's. But those single phase, especially, that's a 3-speed motor. So you can actually switch it three different speeds. And that's what the different color wires are. They're different speeds. And then the brown wires is for the start capacitor. We'll talk a little bit about that. So magnetic motor starter is an electrically operated switch contactor, but it has overloads. And a lot of times it'll be a contactor that they sell, and they'll put the overloads and they'll just mount them on the same plate. So they'll sell the contactor by itself, and then they'll add the overloads. So they won't. Usually a motor starter is not made as one unit, right? You understand what I'm saying? In fact, you can see it on ours. I showed you ours, right? The motor starter. No, our magnetic motor starter that we're going to be using. You can literally see they got a metal plate, so I'll bring it up here. Here's the contactor. So we can use the contactor. So this is put out by Pennsylvania. I don't know. We'll have to look at this. Oh, this is Color Hammer. They make a lot of motor control stuff, relays. And we'll let y'all hold this too. So this is a contactor. They sell this like this. And then what they do is, here's a metal plate, and they'll come up here and mount, here's the overloads down here. So they sell the contactor as a contactor, right? You understand that? And then they mount the overloads on a metal plate, and now this is a magnetic motor starter. And then they wire this into the relay. So that wire that shows you between the relay coil and the overload contacts, you don't have access to that. So we teach that as one unit. Of course, there's the reset. This is a heater. We'll learn there's different types, but these actually use little heaters in here. They're heater coils. And of course, the more current you put in them, the hotter they get. And when they get up to a certain temperature, it literally melts solder. We'll show you how these things work. It's got solder in a tube, and as long as the solder is hard, the thing can't spin. It won't trip. But as soon as it gets hot enough over a certain period of time, the solder melts and it allows it to spin and kick out the overload. And overloads, we'll look at how to calculate these overloads, because usually, especially on companies, so this is for 50. I got what that means. So that tells us a horsepower motor that the contactor. So these are magnetic. This is our magnetic motor starter system also. So they have overloads. So this is a motor starter. It's going to have overloads. Contactors don't have overloads. It don't mean they don't run motors. It's just that the motors usually have the overloads built into them, right? You understand? We see some single phase motors that actually have resettable overloads on them. They'll have a little red button on the back, and you can actually reset the overload, which are neat. They don't do that. So that is a magnetic motor starter. How do I know? Because it's got overloads on it, right? But you can see where they just took a contactor that they sell and do what? Mounted it on a metal plate and turned it into a motor starter. You'll see that all the time. You'll see that all the time. We've got overloads on the manufacturing line on there that's actually mounted off to the side of the motor starters. Which is pretty good. So guys, that's that chapter, and I figured we'd go through it fairly fast. I need to try to get those book. I'll probably, since everybody's buying the book, we can legally make copies, but we can't make many copies, right? You understand? So we understand that some of y'all are waiting on financial aid and stuff like that, and you can't get your lab book. So the first lab that we do is we basically inventory our parts. And of course, they've moved all around. So when we decide which units we're going to use, I think we just about have though, right? Where we're going to split them up. I think we're going to use this one. Then we're going to use this one, that one, and maybe one down in the back. I think we got 5 people in the class. Y'all lucky that they let us teach this, brother. It's going to be real good. We can social distance real easy. We usually like to work in teams because when you get out on a job, you're working with a what? Team, yeah. And like I said, we usually rotate you. We don't work with team people. Well, we try not to get teams more than 2 because once you get that third person in there, sometimes they work together, but more often than not,